Hey everyone, this is Brian. Welcome to week 10 of CSC 143. We are almost at the finish line. There's only one more week after this where you take your second exam, and that means this week is the last week where you actually have lectures from me about content that I'd like you to know for this class. And we also have just one more data structure to review, which is the graph. And the graph data structure is very much the accumulation of everything that we've learned so far when it comes to redirection using references and recursion when searching trees. Graphs can be used to represent a lot of really interesting real-world models and applications. For example, your friend network is a graph. The people you know are like nodes in a graph. The relationships you have the relationships that you have with people, those are like edges within that graph. In real life, you can think of buildings and locations as nodes in the graph. And getting from point A to point B that's using navigation, that kind of algorithm can be applied to a graph in order to efficiently route you from one location to another. I really like graphs. There's a lot going on with graphs that you'll find out, and what you'll discover as you continue your career in computer science is that you'll see graph theory pop up in a lot of places. And it's very much a space dedicated that computer science researchers will dedicate their studies to in coming up with efficient graph algorithms, how to store graphs efficiently, and how to make use of graphs to model these sort of real world applications and ideas. Okay, no real long intro for me today. I take it that you've done the reading from last week and found that interesting. So please do review it. It should be pretty short about functional interfaces, and do enjoy the video. Hey everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be covering the graph data structure, as well as some graph traversal algorithms. Before we dive into that though, I want to quickly recap hash maps and address one additional use case. Remember that hash maps are derived from this observation that we had that arrays are like O of 1 lookup tables that map from integers, which are the array indices, to some generic values that the array is storing. If we can come up with some magic hash function that converts generic data to an integer, then we can store the associated values in a plain array as a lookup table. So the complete mapping goes from some generic type, we hash it into an integer that becomes an index into an array that locates a value. A good hash function has two primary guarantees, the first of which is predictability. Two keys that are equal to each other should have the same hashes. This ensures that the same key is always going to map to the same value. One example of this is the common mapping between a string and another data type, like an integer. Maybe it's like your name to your grade. Regardless of what reference that string is, if I have multiple strings in memory, so long as they're the same string by value, character by character, then they should reference this same mapped number. That is, they should behave as the same key, even if they are two different strings in memory, but they are identical strings according to this equals method. The second guarantee we'd like to see is uniform randomness. That says that two keys which are not equal to each other have hashes that are uniformly randomly distanced apart. Uniform randomness essentially addresses our desire to spread out the key and value pair entries across the hash table. Just because two keys that look alike or don't look alike, just because two keys may look alike or not look alike, should have no influence on how they are randomly distributed across the hash function. This essentially makes it so that we can have a hash table that does not depend on the distribution of the keys in order to have a good distribution of content within the table. Now, uniform randomness is not going to prevent collisions. We've talked about how key collisions, that is, two keys have the same hash value even though they don't equal each other, are inevitable, because we're trying to map the entire universe of generic data to the set of numbers that we have access to. However, that's okay. We're using a technique called hashing with buckets that's going to enable two keys that have the same hash but different values to be stored next to each other. That said, if we can get uniform randomness, we can improve the likelihood that those two keys will bucket to different indices inside of our array and avoid this collision altogether. Given an O of 1 hash function, we can get a randomly distributed array index using the modulo operator with the size of the array. So given some hash value, we can sort of map it to a range of numbers, a range of array indices that fit within the array we're targeting. So as we grow the array, we increase the amount of buckets that we can address, and we also respectively distribute the hash functions, the return value of these hash functions across those respective buckets. Now we just talked about this because the domain of hash functions is the whole universe, and the range of hash functions is finite, which is the Java integer. Collisions are inevitable, and to permit keys that hash the same bucket, that is table index or table row, to be stored within the same hash map, we're going to use a technique called hashing with buckets. We still use an array as a backing store, but each array itself is a linked list that stores key value pairs. So here's an example of that structure. I have an array with 4 buckets. That is an array with length 4. And each index into the array is actually a linked list of key value pairs that is consistent of keys which map to the bucket that have a hash code that associates with the bucket that key lives in, and the value associated with the key. And if there are multiple keys that map to the same bucket according to their hash modulo length, then we will simply chain them along the linked list as shown. Then when we have to look up values associated with a key, we're going to hash the key modulo array length to go find the bucket, and then we'll walk the list to go find the key value pair that has the respective key we're looking for. So even if we have a hashing collision where letters like D, E, and F have the same bucket, maybe they have the same hash code, I can look up the value associated with the key E simply by going through the same process of identifying the bucket in which it belongs, hash modulo the size of the array, which gets me to 3, and then walking the list to go find the key which is value equal the key that I've passed in. So then I can go find the actual value associated with that key and ignore all the other pairs inside the list. We would like to see good randomness to spread values across the buckets, otherwise hash map performance is going to degrade to O of n. Back up here in this extreme example, if I try to shift all these elements, these pairs, into this third bucket here, or the bucket of index 3, if A, B, and C all coincidentally mapped to the third bucket, then performance is going to degrade back down to just a list. I would have to iterate over the entire list to actually go find the key that I'm looking for within the array. The load factor is something which describes how full the hash map will get before it expands. The load factor is designated to be the number of entries divided by the size of the array. So up here, we could say we've got 1, 2, 3, 4, 5, 6 entries and 4 array buckets. So our load factor right now is 1.5, which is actually fairly high. You can see we already have quite a few collisions involved. In fact, we physically cannot fit 6 items across 4 buckets without having a collision. So what we can do is we can expand that hash map to spread out all the key value pairs across more buckets and try to minimize the amount of extra iteration that has to happen when we are examining a particular bucket. When we expand a hash map, we rehash every key to determine its new location based on the new length of the underlying array. Then we move that key value pair into its new spot. I like to say that hash maps are magic because they have O of 1 insertion, O of 1 lookup, and O of 1 removal, if we have good hashing function and good even distribution. That being said, hash maps are not ordered like lists are, and they don't have a natural sorting without some supplemental structures. What I mean by this is we can't quite make something like a binary search tree out of the hash map itself. It doesn't really make a ton of sense unless we build that tree next to the hash map as a means of organizing the data. Let's go visit an old friend. Remember the hash set from project 1? A set is a collection of objects without duplicates. The interface looks something like this. Add, which inserts a value into the set, preventing duplicate values, that is any value that is already equal to the value we're trying to insert. There won't be more than one of those inside the set. Contains simply returns true if the value is in the set and false otherwise. And remove removes the value from the set. Okay, so a set is just a bag of items that has no duplicates. A hash set is actually just a hash table that gets us O of 1 insertion, lookup, and removal. And the way we're going to do this is we're going to have it such that the objects in the set are hashed and mapped to meaningless values because the object key alone, the presence of the key, indicates that the object is in the set. We can implement a hash set by leveraging an existing hash map. Let's go through what I mean by that. Let's go visit hashset.java. Okay, here in my hashset file, I've imported the Java library hash map, and I've defined my hashset class as being a generic type T, so the set stores values of type T. As one of my instance variables, I'll define an internal map that is a hash map, the Java library hash map that maps T's to integers. This choice of integer as the value type for the hash map is meaningless. Ideally, we prefer smaller values. And I say it's meaningless because when we build this hash set, we're going to make it so that so long as the key is somewhere present in the table, we're going to consider the item as being in the table. So the value it actually maps to doesn't matter. It's meaningless. We should just pick whatever value is small. Integer is generally pretty small, so let's go with that. All right, so now that we have this internal map going, let's go ahead and fulfill that interface I talked about in the README. Add, contains, and remove. And we're going to say that so long as there is any value associated with the key that I passed in, we're going to consider the value to be within the set. So my add method is going to take the value I'm trying to insert into my set and associate the value with some arbitrary value like 1 here. So in my internal map, I'm going to associate every value in my set to the value 1. And then for my contains and remove, I'll simply ask whether or not that 1 is there. It's like a little flag indicating that the value, the key, is in the set. So my contains method simply asks, is the value that I'm asking about, is it a key that maps to 1 inside my internal map? If it's not null, that must be the case, so it must be true. If it is null and get returns nothing, then it's not in the set. Then the remove method I pretty much get for free. HashMap itself has a remove method that removes the association between the key and the value that I've got stored in the map, where the argument is the key. So here I'm taking the key out of the map by simply calling that remove method. I've got a size method here that just returns the internal map size. So essentially what we've done is we've taken advantage of the fact that internal map, this hash map here, which associates keys to values, is always going to guarantee that so long as there are two keys that are equal to each other, they're going to map to the same value. And remember, the contract of HashSet tells us that we should not have duplicate values that are equal to each other. We should only have up to 1 inside the set. A set is a bag of items that has no duplicates. So I'm taking advantage of this map property that says two keys that are the same value should map to the same value by its inherent ability to avoid having duplicate values associated with the same key. Now let's go visit my main method to see a couple of usage examples. Here I've declared a hash set of numbers. I add some numbers, 5, 10, 3, 10, and 5. So the three unique values are 5, 10, and 3. So I should expect to see 3 numbers inside the set, it containing 5 and 3, and not 99. Great, that's exactly what I got. So all in all, the hash set is nothing too magical. It simply takes advantage of that predictability property we saw inside HashMap keys. Remember that hash sets, though, still do depend on that internal hashcode method that Java has, where hashcode is the underlying hash value that the instance maps to. Without a well-defined hashcode, HashSet cannot support the object because it cannot be used as a HashMap key. It is true that every object in Java does come with a hashcode method that's inherited from the top-level object, but it's not a meaningful one. It doesn't give us predictability nor randomness based on how we define the fields inside of our class. One way to think about that is, remember that building class or that business class we built in Project 1? Well, having a hash code of the business without considering things like its name or its address is not meaningful because those name and address properties define what the business is. Similarly, if I have something like an integer, using the default object hash code may not give me something that's at all relevant to the integer value itself. The underlying value should dictate what the hash code is. So you're going to have to go about defining that hash code method for your own custom classes if you'd like to use them inside these structures like HashSet and a HashMap key. All right, let's go learn a new structure, the graph. Let's first think back to linked lists and trees. With singly linked lists, we were restricted by this limitation that each internal node would only point to a single next node. We lifted this restriction to form trees, which are like linked lists, except that a single node may then point to any number of next child nodes. A further limitation on trees was that trees may not contain cycles. A child node cannot ever point back to a parent node in a path. This gives us some interesting guarantees, like if we do a recursive search on a tree, we're guaranteed to eventually terminate because we'll eventually reach a leaf node, which is one of our base cases. We also know that paths are guaranteed to have a limited length. The maximum path length would be from the root to the deepest leaf. Now, what happens when we take away this acyclic limitation? We get a new structure, the graph. A graph is a data structure composed of independent nodes, where each node can point to any number of other nodes in the graph. Formally speaking, a graph is composed of V and E, where V is the set of vertices, or nodes, in the graph, which can hold payload values, and E is the set of edges, where each edge connects two vertices. The set of nodes, which a node is connected to, are called neighbors. Let's go take a look at the whiteboard to see a graph structure. Okay, G is composed of V and E, so here's my entire graph, G, and my V and E are the vertices and edges respectively. So here in my triangular graph, I've got nodes A, B, and C, where A and B are connected, B and C are connected, and A and C are connected. We can define that as first listing out the vertices. I've got three vertices, A, B, and C. Then my edges take me from A to B, B to C, and A to C. We call this an undirected graph. There are no arrows on either side of the edges, so there's no specific direction that each edge is pointing towards. In the set that associates vertices to other vertices inside my edge list, the ordering in which the vertices are stored, A and B or B and A, that's arbitrary if my graph is undirected, because it doesn't really matter. There's no arrows, there's no specific direction. We can think of these edges as two-way edges. Now let's go look at a more advanced example. Here my graph has four vertices, A, B, C, and D. I've got several edges inside this graph. We see these edges not only have direction, they have an arrow at the end, they also have a weight, a number associated with the edge. So here I see A has an edge linked to B with a weight of 2, but this is a unidirectional edge. There's no way, or there's no link that takes me from B back to A. Over here, C actually has an edge pointing back to itself with a weight of 2. This is perfectly valid in terms of graphs, and not valid in terms of trees. Down here, node D has several edges, incoming as well as outgoing, and node D actually has two edges linked to node C here. It's got an edge that leads from D to C, as well as an edge that leads from C back to D. So this is something we call a weighted directed graph. It's weighted in the sense that every edge has a weight associated with it, and it's directed in the sense that edges have a direction. They specifically go from one node to another node, and not the other way around. However, if we would like to describe an edge that goes between two nodes, we can define two separate edges that do that. So here formally, my list of vertices is A, B, C, and D, and my list of edges takes me from A to B of weight of 2, B to C with a weight of 3, C back to itself with a weight of 2, B to D with a weight of 6, C to D with a weight of 1, D to C with a weight of 1, and from D back to A with a weight of 4. We've seen how edges themselves can have certain properties. Edges can be directed, one-way, or undirected, two-way, kind of like a one- or two-way street in real life. Edges can have a weight, sometimes known as a cost to use. This is not in terms of big O performance, but in terms of semantics. We could say that a highway in real life supports many more cars and can be traversed much faster than a side street or an alleyway. So perhaps the highway is cheaper because I can get past it much faster, but a side street or alleyway is more expensive because I go much slower in terms of time. Graphs have a lot of real-world parallels and use cases. Your social network is like a graph. The people are nodes, and connections are edges. Mapping and navigation. Locations are nodes. Streets are edges. Networking. Devices are nodes. Edges are the connections between nodes forming the internet. Trees are graphs. Trees are just acyclic graphs. By definition, a tree is a directed acyclic graph. I do have a remark here, which is graphs are unfortunately named, much like how heaps are unfortunately named and clash with the heap, this block of memory that we use to store object indices. In computer science, we say that a graph is a data structure. In Microsoft Excel, we say a graph is a chart. Know the difference. Here in this class, we're going to always be referring to graph as this data structure. Don't get it confused with the graph that looks like a chart in a spreadsheet. Now let's go over how we actually represent these graphs in programming. The most natural way that we know of is to store this graph like we stored all the other structures, like the linked list and the tree. We'll construct a bunch of node objects, and then we'll use references to represent edges. Let's go take a look at a few examples. Here's my graph node interface. The graph node interface is going to describe nodes which have a value and have neighbors. So I've got methods like setValue and getValue, addNeighbor, which associates another node to this node, removeNeighbor, which takes that neighbor away, and getNeighbors, which returns a collection of graph nodes. Let's go see this interface implemented in the directed graph node class. Here I've got public class directed graph node implementing graph node, so it's got to go fulfill all those method declarations. We'll give it a value field and a hash set of neighboring nodes. There's also this ID field I have in here. We'll talk about this in a little bit. The ID field is not something that we really want to have, but it's useful for testing purposes, and we'll see why in a second. So don't think too hard about it right now. Just think about the value that we have in this node and the set of neighbors that we are associating with it. My directed graph node constructor will take an ID and a value, assigning those fields respectively. I'll have setValue and getValue that simply assign and return the value. My addNeighbor and my removeNeighbor methods are simply going to add the new neighboring node and remove the neighboring node from the set of neighbors. And my getNeighbors method should just return my neighbors set. Here I've gone ahead and also implemented an equals method. Remember that equals should perform value-wise equality. So I should go figure out if the underlying values, the ID, the value, and the neighbor set are the same to determine if two nodes are equal to one another. I've got the usual guard statements, the null check, the self-equality check, and the class cast check. I perform my cast, and then I'll go validate if the ID and the value are equal to each other. For now, I'm going to keep this definition simple and ask if the ID is the same. We'll talk about the ID in a little bit. We'll see it in the test cases. And we're going to use ID as a field to uniquely identify nodes. Now, you might be a little suspect of this ID field, and we'll talk about why it's not really ideal in a little bit, but we're going to go treat it as a unique identifier and also validate the value as well. If we don't have this ID field, we should go use something like collection equality to go validate the neighbors of both nodes being equal. But for now we do, so let's go ahead and take advantage of that. Generally speaking, whenever we override the equals method, we should also override the hashcode method. And this is very much due to that predictability guarantee that we like to see out of hash functions. Hash function predictability tells us that so long as two instances are equal to each other by value, then they should have the same hash code. So by nature of us updating the equals method to refer to properties like ID and value as reflective of the internal state of the instance, we should make sure that our hash code also refers to those same properties such that when these properties change, their hash code reflects that change. And similarly, when two object instances are equal to each other, according to their equals methods, their hash codes should result in the same thing. Now, when we look at this hash code definition, you're going to see some things that you may not be familiar with. I've got the ID field multiplied by a prime number. I take the hash code of that. I exclusive OR it with the hash code of the value. It's okay. I'm not expecting you to understand how a hash code gets implemented. That is beyond the scope of this class. Instead, I'd like you to examine what I've done here, just to, I guess, appreciate on a surface level how I'm still meeting the requirements of randomness and predictability. We'll address predictability first. I see that given a static ID and a static value, my hash code return value should not change. If the ID is a fixed value, a fixed constant, multiplying it by 31 is going to produce the same value every time. Taking the hash code of this expression should produce the same value every time, and then the hash code of the value should also produce the same hash code each time. So this entire expression should stay the same so long as the ID and the value fields remain the same. The other guarantee that we're looking for is randomness. The hash code on both fields here are random according to their standard library implementations. The hash code on the first expression comes from the hash code of the long definition. Remember, long is like a wide integer. And the hash code for the second one is just whatever I assign in the value here, so I'm expecting that the generic type of the value has a well-defined hash code already. The exclusive OR operator is going to take the bitwise exclusive OR of these two integer constants, and that's going to give me a set of bits that are about as random as the hash code of the first expression and the second expression. It's okay if you don't quite understand what's going on here, that's all right, but I do hope you appreciate how I'm fulfilling the requirements of the hashcode method with this expression. Okay, now let's go take a look to see how this directed graph node gets used in directed graph node test.java. We're going to start out with this sample graph that I've diagrammed here with this beautiful ASCII art. And I've described how in this directive graph, all edges point downwards except the edge from 12 to 10. It's like a water slide and a ladder. So I've got a node 10, it has two children, 5 and 9, each of which have children of its own, but the same node, 12, and 12 points all the way back up to 10. So 10 points down to 5 and 9, which both point down to 12, and 12 points back up to 10. Okay, we're going to describe this graph structure in a very similar format to how we described linked lists and trees. We'll go about constructing a whole bunch of individual nodes, and then we'll link all those nodes together based on the relationships. So I have a node 10, I'll give it an ID of 1 and a value of 10, a node 5 with an ID of 2 and a value of 5, a node 9 with an ID of 3 and a value of 9, and a node 12 with an ID of 4 and a value of 12. Then to organize my little water slide, I will add 5 and 9 as the two immediate neighbors of 10. We can kind of think of it as children of 10. I say that because adding a neighbor to one node will not cause the other node to have the original node as a neighbor. So 10 sees 5 as a neighbor, but 5 does not necessarily see 10 as a neighbor because I've not added 10 to 5's neighbor list. So adding neighbors is just one directional for now. 10 has a neighbor of 5, also a neighbor of 9. Then 5 and 9 are both going to point to node 12, and then 12 is going to point back up to 10, forming our little diamond diagram here with 12 pointing all the way back up to the 10 node. In my first test, the diamond test, we see just a one-liner to retrieve a single element out of the collection, and we're going to do this to assert that indeed 10 is a neighbor of 12. My one-liner simply says get the neighbors of 12, get the iterator, and then invoke the next method. Remember, the iterator is a method available on all collection types, which are iterable. That's going to give me an iterator on the way out, and I can invoke next to retrieve the first element out of the iterator, which would be 10, which is the only immediate neighbor of 12. This is okay since we know 12 only has one neighbor. Not really general purpose, I just want to assert how the neighbors of 12 include 10. Okay, now we're going to try and use this little water slide structure with some recursive algorithms. And we'll start out with this tree sum algorithm. And we're going to talk about how recursion with graphs is a little bit different than recursion with trees. So here my tree sum algorithm is going to assume that the node I'm passing in is actually a tree node. I know it says directed graph node here, but as a mental exercise, we're going to write this as if we think it's just a tree, because that's what we know how to do already. We have our base cases. If the root is null, it's empty, then the sum of the items in the tree is going to be 0, okay? If there are no neighbors of this root node, then the sum of all the items in the subtree is just going to be the value immediately placed at the root. So return that. Otherwise, I will add up all the values, including the current root value, by taking the current root value and adding it to the recursive sum of all the neighboring nodes. So this is very much my recursive case, where I take my base case solution, my sum of the starting with a root node, and then I walk every graph node nearby by invoking the for each loop against the get neighbors method. And then I'll add to that composite solution the recursive tree sum call of all the neighboring nodes. Then finally I return sum. Okay, let's see how that works. Let me go ahead and comment out these extra lines here. You'll see why they're needed in a moment. But let's go ahead and invoke tree sum of 10 and expect to see 36 on the way out, because 10 plus 14 plus 12 gets me 36. So when I assert tree sum of 10, I should get 36 on the way out. And when I run it, let's see what happens. Oops, I get a Java lang stack overflow error. Well, well. What seems to have happened is I've somehow encountered an infinite loop inside my recursive function. The stack overflow occurs because my subproblems never dissolve down to a base case and prevent further recursion from happening. Why is that the case? Well, let's examine this recursion process step by step. If I call tree sum of 10, 10 is going to recursively invoke tree sum on 5 and 9, which will then both recursively invoke tree sum on 12, and then 12 is going to go recursively invoke tree sum of 10. That's going to start the whole cycle over and over again. The outcome is that the recursion will never end, because they will never hit a base case where there's no more children associated with a given node. Remember that we wrote this function kind of assuming that the root node was a tree, or represented the root node of a tree. But this is actually not the case. We actually have a graph here. Graphs do not have the limitation that they must be acyclic. So the outcome is that we have an infinite loop, because the recursion will keep on going back to the initial function call to the root and then start repeating the recursion process over and over again. Okay, we're going to start to break up this loop by first removing the initial loop part, where I take away 10, 5, 9, and 12's link all the way back up to 10. So in theory, I should get the sum of just the 4 nodes 10, 5, 9, and 12 in the tree, and the recursion should terminate because 12 is not going to have this neighboring link anymore. When I run this test, what do we get? We get not a stack overflow exception, but an assertion failure, where the value I get on the way out of that call to tree sum is 48, and I expected the value of 36. What happened? How did we get 48? Well, let's trace the recursion. I've got 10, adding the recursive calls of 5 and 9, and 5 and 9 are both going to count the recursive call to 12 on their own. So in essence, what will happen is 12 is going to get counted twice. I've got 10 plus 14, then plus 24, rather than just 12, which is why I'm getting 48 on the way out of tree sum instead of 36. This assumption that the node that we passed in was for a tree, which was acyclic, has once been violated again, because in a tree, I'm never going to expect a node to have more than one parent. But here we see how two nodes in the graph point to the same node as another neighbor, causing us to count that same node twice. Let's eliminate the path from 9 to 12 to eliminate that second count. That means I only have a path from 10 to 5 and 10 to 9, and a path from 5 to 12 remaining. I run my test, and I see it finally passes. So the lesson to be learned here is that although tree recursion is rather intuitive to work on graphs, it's something that we think should work because we've taken care of the base cases and we do the recursion to go walk the remainder of the graph. We see how that acyclic guarantee of the tree made it a little bit easier for us to reason about how the function would eventually terminate. But if we have a loop in our graph, a cycle in our graph, it's possible that our function will never terminate, or it's possible that there will be multiple references to the same node, and that node will be counted twice. I'll uncomment these lines here so I reassemble the water slide after this test completes. All right, now let's go about modifying that tree sum method so that it applies to graphs and is going to correctly compute the sum of the values inside the graph. I'll start out with this helper method, graphSum. I'll once again take a root node, but I'll pass in an additional argument to this function called graphSum node duplicates called a HashSet. And what the HashSet is going to do is it's going to maintain a visited set to avoid duplicates. The visited set is going to be scoped inside the stack frame and going to be referenced by all recursive calls. So remember that in Java, everything is a reference. Everything is also passed by value, but as a reference. So when I declare a new hash set here, I'm getting a reference to a hash set in memory, and that's going to be present in all calls to graphSum of node duplicates, so long as that same hash set reference gets passed along recursively. So this hash set that I declare in the very beginning in my helper method is going to be the same hash set that I see overall. That's going to essentially enable these recursive functions to communicate with one another in a way such that they can avoid duplicates among each call. Let's see how this graphSum node duplicates method is defined. I take two arguments, a hash set of directed graph nodes of integers, that's my visited set, and a second argument, which is just my root of my graph. I'll kick things off with the same base cases. I'll check if the root's null in case I return empty, but I'll also add on this additional base case, which is if the visited set already contains the root, that is to say I've already seen and counted the root node, then I should return nothing because I don't want to keep going down this path. I've already visited this path, so return 0. This is going to fix that infinite loop problem that I saw earlier because I'm going to reach a base case because if I happen to hit a node that I've already seen, I will not count it any further. I've got a same base case where if my root has no neighbors, I'm going to go ahead and add the value that the root is and return that immediately. Also, let's go ahead and add that root to the visited set. I also do that down here, and I see a simple optimization I can do in my code is I'll move this line up here because I know it's going to get called regardless of whether or not the if statement expression gets evaluated inside, or the body of the if statement gets evaluated. So let's go ahead and simplify that real quick. I'll always add the node that I'm currently on to the visited set, and then I'll go take care of the rest. Okay, so if I reach line 105, it means I've hit my recursive state, my recursive case. To compute the recursive solution, I need to take my base case solution, which is the solution at the current location, which is of course my roots value. I'll declare that as sum. Then I will walk my neighboring nodes, and I will add to this composite solution the recursive call of graphSum node duplicates with the same visited set that I had from my argument, and then my neighboring node. Then finally, when I'm done recursively computing the solution, I will return the composite solution, the total sum of all the nodes in the graph. Here we go again. I've got my water slide. 10, 14, and 12 gets me a total sum of 36. And then when I call graph sum, I should expect that assertion to be true. Perfect. So as you can see, converting a recursive tree formula into a recursive graph formula is not too much of a challenge. We can take advantage of this HashSet structure that we just learned about to avoid running into duplicates, and apply the same recursive search patterns we saw with trees into graphs. This way of storing graph nodes as independent instances and then defining edges as the references between instances is perhaps the most natural way to store this graph, because we've seen a similar pattern with linked lists and trees. However, there are other ways we can store this graph and represent its state that are worth reasoning about. The first I'd like to mention is the two-dimensional array, which is called the adjacency matrix. Every node is represented as a row or column, kind of like a spreadsheet, and a value is stored in the array if an edge exists between two nodes. Let's take a look at this diagram. I've got 4 columns and 4 rows, where each column and row represents a single node. So I've got node 0, node 1, node 2, and node 3. And I'm essentially asking whether or not, within each cell, I'm asking whether or not there is an edge between the row node and the column node. So the tail nodes are represented, the tail of the edge are represented by the rows, and the tip or the head of the edge is represented by the columns. So here I see node 0 does not have an edge back to itself, but it does have an edge leading to node 2. Node 1 has an edge leading back to itself, as well as an edge leading to node 3. Node 2 has an edge leading to node 1, and node 3 has an edge leading to node 0. Let's go take a look at the whiteboard to see how that looks. Okay, here's my diagram. I've got node 0, which has an edge leading to node 2, which is down here. Node 1 has an edge leading back to itself, as well as an edge leading down to node 3. Node 2 has an edge leading to node 1, which I see in this diagonal here. And node 3 has an edge leading up to node 0. This sort of two-dimensional representation of a graph doesn't particularly scale well because it gets us to big O of n squared storage. For every single node n, if we have n nodes in the graph, we're going to have to represent all the relationships between that node and all other nodes in the graph, which gets us n squared representation. However, they are simple enough to implement, and they're easy to iterate over. If you'd like to iterate over this whole graph structure, just do a couple for loops. You don't even have to use recursion. You can imagine other ways we can store graphs in code that go beyond the two representations we've seen here. One thing we can do is actually build an edge object and have that edge store the references between two nodes. That tends to make things more complicated because it requires that nodes have references to edges and edges have references to nodes. So there's a lot of extra linking going on, but it can be useful when you want to represent additional state amongst edges, such as what the weight of each edge is or whether an edge has been used before. Okay, now let's talk about graph traversal. We know how recursion works for trees, and we saw an example of that with the tree sum algorithm. We define a base case that solves a local subproblem. A tree with no child nodes is easy to solve, or an empty tree is just a trivial solution. Then we define a recursive case that combines subproblem solutions, such as walking all the children and combining the results into a meaningful solution. And then we do that third praying step. We're going to assume that the base case works and that the recursive case is going to combine those composite solutions and eventually shrink our overall problem into a base case that will eventually return back up. We saw that when we try tree recursion on graphs with that tree sum method, that we're going to end up hitting duplicates. And we may count nodes twice, or we may actually end up recursing infinitely, causing a stack overflow. So we can't quite drop in tree algorithms directly where graphs belong, because trees are acyclic and graphs may not be. So to avoid processing the same node more than once, we'll use that hash set we learned about that's going to contain a visited set of all the nodes we've seen so far, and avoid revisiting the same node if we've seen it already. So now that we're comfortable with traversing graphs using recursion, I want to go over some famous graph algorithms that solve some of these well-known applications of graphs in the real world. And perhaps the most well-known application of graphs is real-world navigation, such as with Google Maps. We can consider nodes as locations, buildings, parks, etc., edges as streets. These edges are one-way, two-way, highways, etc. And we say that the cost or weight of a particular edge is the distance plus time required to travel down that street. So it's like the cost of having to go down that road compared to all the other roads on the graph. Let's go visit the whiteboard for a quick example. Let's suppose we have a set of nodes and a set of edges, and node A here is my home, so it's where the starting point is for all my searches and navigation. Then if I want to get to any of these other nodes, B, C, D, E, or F, which maybe represent restaurants or stores, I'm going to have to go find an efficient route that takes me across the edges that lead up to that node to reach the destination. We can think of cheaper edges as maybe shorter roads or faster roads like highways, and more expensive edges as roads that are longer or more costly to traverse. Maybe it's like going up a hill. So perhaps rather than going up a steep hill to get from node A to node D, I could instead go around the hill and first go from node A to node C and then hit node D. So now we ask this question of how do we minimize the cost of traveling from point A, my starting location, to any other node B? In other words, what is the shortest path that gets me from A to B? The searching algorithms that we've learned so far, like depth first search and breadth first search, are a good start, but they're going to assume all edges have the same weight. They don't count that weight variable during traversal. The outcome is that we're going to perhaps take less than optimal paths during our search. And although maybe we'll eventually find our destination because these are both exhaustive search algorithms, they're not very efficient in the way that they will look in the wrong direction, possibly first, and go very deep in that direction before it comes back around to look a different way. So here's a big idea. Let's recursively search the graph and process nodes in the order of how cheap they are to access. One way of thinking about this is getting to the parking lot nearby is cheap, but getting to the top of Mount Everest is hard. So if we'd like to take the trek to Everest, let's first get to the parking lot and get in our cars. An algorithm which pursues the best short-term case first is known as a greedy algorithm. Dijkstra's algorithm is a well-known greedy algorithm invented by Edgar Dijkstra in 1956. Dijkstra was faculty at the University of Texas, where I'm from. Dijkstra solved the shortest path problem in weighted graphs. Here's a bit how it looks. We're going to start out by initializing a map D of distances that maps nodes to their best known minimum distances. So we'll start out by declaring the root node to be a distance of 0 away, because of course we're already at the root. And then we'll say all of the nodes are going to start out as infinity because we don't know yet how long it takes to get there. Then we'll initialize a priority queue, let's call it Q, with the root node only. And the priority of each node is the minimum distance to reach that node that's known. So we'll just use this lookup table D to represent the priority of every node inside the queue. The root node has a priority of 0, so it's our highest priority. We're going to visit it first. Then we'll initialize a visited set, a hash set perhaps, S, that's going to start out as empty because we haven't seen anything yet. Now here's our general loop. While we still have nodes in the priority queue, we're going to pop off a node V from that priority queue, If it's already been visited, we'll just skip this node. Otherwise, we're going to say that we've visited this node already, and then we'll go examine all the neighboring nodes of this node. And if it just so happens that the best known cost to reach my current node, the node I'm presently on, and the sum cost of the edge it takes to get from my node to the node that I'm examining, this node U, that's the neighbor of V, if that's less than the best known cost so far we have to get to that node we're examining, then we will insert that node we're examining into the queue, and then update the best known cost for reaching that node with this new cost of the cost it takes to reach us, plus the cost it takes to get to that neighboring node from our present location. We'll repeat that process over and over again until eventually we've processed all the nodes and the queue has emptied, and we will return the table D that indicates the minimum cost it takes to reach every node. Okay, let's go to the whiteboard and see how all this works. So Dijkstra's algorithm's goal is to find the shortest path it takes to get from a root node to any location on the graph. And I've got a copy of the pseudocode down here that we can follow along with. And we're going to start out with root node of A, and we're going to go find the shortest cost it takes to get from A to every other node in the graph. So the initialization step for Dijkstra's told us to initialize the root node as a cost of 0, and then all other costs as infinity. So go ahead and write in 0 as the cost of node A, and then I'll leave the rest blank because I know they're infinity. And then the other thing is I'll need to add node A to my queue, my priority queue, where each element's priority is its best known cost. So we'll start out with node A in my queue, and we have nothing else. Okay, so now the algorithm tells us, well, the queue is no longer empty, or is not empty. We will pop off a node off the priority queue, and then we'll go visit all of its neighbors, so long as we haven't seen that node already. I'll go ahead and use little check marks to indicate that a node is going to be added to the visited set. So I'll visit A, and then I'll reach this line of having to insert that node A into the visited set, and now it's time for us to look at all the neighbors of A. A has 3 neighbors, B, C, and D. We'll just go through them in that order. Let's go look at node B first. We're going to ask ourselves if the best known cost to get to ourselves, which is 0, plus the edge cost from ourselves, A, to B, is less than the best known cost to get to B, then we want to update that best known cost with this new found cost. So this is definitely the case. The cost we know to get to B is infinity because we don't know how to get there yet. The cost to get to A is 0, and the edge cost to get from A to B is 2. 2 is definitely less than infinity, so that means we've found a better route to get to B than any other route that we've known so far. We'll go ahead and insert that node B into the queue, and then we will update the best known costs to get to B in our table. Okay, the next neighbor of A is going to be C. Let's go take a look at that. The cost to get from A to C is 3. 3 is less than infinity, so we insert C into our queue, and we update our table accordingly. The third neighbor of A is D. We have a best known cost to get to D as infinity. The new cost we've discovered is this route with a cost of 5. We will insert D into the queue and update our table accordingly. Okay, now that we've done traversing all the neighboring nodes of A, let me go ahead and remove it from our queue. We technically did it at the very top, but this is kind of our way to keep track. And then we have to go look at which among the queue elements is the cheapest to get to so far. Remember that the priority of the queue is dictated by the cheapest best known cost to get to those nodes in the queue. Right now it seems to be in the same order in which we traverse them. B comes first at priority of 2, C then priority of 3, and D at priority of 5. So now let's go back to the top of the loop. While the queue is not empty, we will pop off B from the queue, and we will go examine all of its neighbors. First, we'll add it to the visited set. I'll give it a check mark here. And then we'll go look at neighboring nodes of B. Let's go look at A, which is the first neighbor to the left of B. It costs 2 to get to B, and 2 more to get to A from B, for a total cost of 4, but the best known cost to get to A is 0, So we don't have a better route. This also makes sense just kind of logically speaking. If we go from A to B and B back to A, we're going to cost more than just staying at A. So in that case, we skip adding A to the priority queue again and updating its cost. The next neighbor of B is C, and we see how it takes 2 to get to B, then 2 more to get from B to C, for a total cost to get to C through B. But the best known cost to get to C so far is 3, and that's less than the new cost that we've discovered of 4. So once again, we skip adding C to the queue, and we skip adding C to the table. That finishes all the neighboring nodes of B, so now we're done. We pop off B from the queue, and we go on to the next node. We enter the top of the list, or the top of the algorithm again. While the queue is not empty, we'll remove node C, and we'll go examine all of its neighboring nodes. And we'll start off by adding C to the visited set. Okay, C has several neighbors, A, B, D, E, and not F. It's just got A, B, D, and E. And we'll go through the same exercise of looking at all the nodes and making sure that we have the best known cost to get to them. We will start out with node A. It costs us 3 to get to A, it costs us 3 to get to C, and then 3 more to get from C to A. For a total cost of 6, 6 is not better than the best known cost of 0, so we will not update A's best known cost. To get to B through C, that costs 2. To get to C, it costs 3, so we have a total cost of 5. But the best known cost to get to B is 2, so we do not update that either. Let's go look at node D now. It takes 3 to get to C, 1 to get to D through node C, and 3 plus 1 gets us 4, which is less than the best known cost we have of D, which is 5 so far. So that means we need to update this known cost in the table with this newfound cost that we can get from going to A to C to D, a total of 4. So I will insert D into the queue again, and I will update its cost in the table with this newfound cost through C. All right, one more neighbor of C, which is E. It takes 3 to get to C, and 4 plus 3 to get to E through C, for a total of 7. And the cost to get to E so far is infinity, so indeed we found a new route. Let's update that and add it to the queue. Okay, now we are done processing all the neighbors of C. Next on our list of priorities is D. So let's go ahead and add D to the visited set and start looking at D's neighbors. D has the neighbors A, C, and F and E. If we go look at neighboring A, we see how it takes 4 to get to D, then 5 more to get to A, for a total cost of 9, definitely not better than 0, so we skip that. To get to C, it costs us 4 to get to D, then 1 more to get to C, for a total cost of 5, which is not better than the best known cost of 3, so we skip that one as well. To get to F, let's see, it takes 4 to get to D, then 5 to get to F, for a total cost of 9, and that's less than infinity, so indeed we found a better route to get to F, for a total cost of 9. And we'll add F to the queue. And then one last node neighboring D, which is this node E. It takes 4 to get to D, then 2 more to get to E through D. So 4 plus 2 is 6. Best known cost to get to E so far is 7. Let's go ahead and update that cost by adding E to the queue again and updating its table with a total cost of 6. Okay, now I'm done looking at this node and all of its neighbors. If a node appears more than once in the priority queue, that's okay. They will be organized in terms of priority, and if the node is already in the visited set, as we see here with D, then we'll just go ahead and continue and skip that node. Next, among the priorities, we see E and F having 6 and 9 priority respectively. E is going to come first. Let's go add E to the visited set and then look at all of its neighbors. Neighboring nodes of E are C, D, and F. If we go look at node C, it costs 6 to get to E, then plus 4, a total of 10 to get to C through E, definitely not cheaper than the best known cost of 3. To get to node D through E, it costs us 6 to get to E, then 2 more to get to D for a total cost of 8, definitely not better than the best known cost of 4. And to get to F, well, it costs 6 to get to E, and 1 more to get to F from E for a total cost of 7. And 7 is indeed better than the best known cost of 9. Let's update that cost and add F to the queue. Okay, that's all the neighbors of E. Just one more node to go, which is F. Let's go look at F's neighbors. F has 2 neighbors, D and E. Don't forget to add F to the visited set. D is not going to be cheaper, given that it costs 7 to get to F and 5 more to get back to D, for a total of 12. Definitely not cheaper than the total cost of 4. And similar story with going back up to E. It costs 7 to get to F, 1 more to get to E for a total cost of 8. And a total cost of 8 is not less than a total cost of 6 here. We clear off F from the queue, E and F have already been visited, and now we are done. We have figured out the best cost it takes to get to every other node from the root node of A. Now you might be wondering, now that we have this table, how do we actually figure out how to get from every location to every other location? And this is what this additional from column is going to keep track of us for. We didn't explicitly talk about this in the algorithm. Right now the algorithm only returns this table that indicates the cost to get from the root node to every other node, but it doesn't indicate to us the path it takes to get from the root node to every other node. We can augment this algorithm such that it keeps track of this path simply by indicating which node is the parent node of itself that represents the node that it takes to get to that node that we're examining. So what I mean by this is, let's go take a look at node B again. The cheapest way to get to B was through A. When we updated that table, D, with that cheapest node, we can keep track of the predecessor node, the parent node, along the path to get to B, so that we can later use it as a way of navigating. So we will say, to get to B, we went through A. Then let's go look at these other nodes. Node C, we got there through A as well. Node D, we had gotten there through node C, which had gotten there through node A. So we'll go ahead and say node D's predecessor was C. When we updated E's table, we did it through the path through D, which itself we found the path through C and A. So E's predecessor could be called D. And F's predecessor, well, we updated F's cost with the best known cost to get to E. So F's predecessor would be E. Now that we have the predecessor nodes of every node in the graph that generated their best known costs, we can go back through these predecessor nodes to generate a path to any node in the graph that's minimum cost from the root node. So let's say I want to get to node F. F's predecessor was E. As soon as I figure out my pen here. F's predecessor was E, which itself had a predecessor of D, which had a predecessor of C, which had a predecessor of A. So now we can see how, if we take the reverse of this list that we've generated, we can get to node F in the most efficient way possible. We go from A to C to D to E and then F. So that's how Dijkstra's algorithm is going to figure out the minimum cost it takes to get to every node, as well as the actual path it takes to get there, by keeping track of what node was used to generate the best available cost to get to the target node. Okay, I want to make some observations about this Dijkstra's algorithm exercise. The first one I'm going to point out is that when a node gets popped off of the queue, the fastest path to that node is known. As soon as we remove a node from the queue and we start examining all of its neighbors, that means that we have found the best route available to that node in existence. And we can pretty easily theorize about why this is true, which is if there were a better path available after we popped off this queue, then we should have seen that already inside of our queue. Remember that our queue is going to prioritize nodes based on what is the cheapest path available to the nodes that are in the queue. So if there were a faster path, then we would have seen this node already. So when the node does get popped off, it means we've exhausted all of our options to get to that node and we've found the best path so far. We did see how a node can appear in the queue more than once, but it only gets processed once thanks to that visited set S. Finally, Dijkstra is just not going to work with negative edges, like taking a slide down a hill perhaps. You could come up with some graphs that break Dijkstra's algorithm because it's going to rearrange nodes in the priority queue and violate this assumption that we say that the fastest path to that node is already known. If you happen to find one of these water slides, for example, we might end up discovering a cheaper path to a node after we've already visited that node and popped it off the queue. The big O of Dijkstra's depends on the choice of the priority queue. We can probably use a heap in this instance. In fact, I think we should use a heap because it's well designed for priority queue use. At least we know that the performance is going to be greater than big O of the number of vertices plus the number of edges. And I think this is a pretty reasonable thing to assert because Dijkstra's algorithm is going to have to go visit every node at least once, and among those nodes, it may have to go visit all the edges surrounding those nodes. So in terms of performance, it's going to scale up relative to the quantity of vertices and the quantity of edges. Another real-world graph problem, with billions of dollars at stake, is formally known as the minimum spanning tree problem. Imagine you are in the utility business. You are connecting energy, water, oil, and internet to the nearby houses in the neighborhood. We have the requirement that every house must be connected to the grid, and we want to minimize the cost of actually laying down the pipe or the fiber wire. With these utilities, the cost to reach any specific house doesn't really matter, so long as the house itself is connected to the grid at some point. One way of thinking about this is it doesn't matter how close your house is next to the internet hub, so long as your house is at some point connected to the fiber lines that will eventually reach the internet. The minimum spanning tree is a subset of nodes and edges in the graph such that, number one, all the nodes in the graph are connected to all other nodes by a path, and number two, the sum of cost of all the edges is minimized. We see the minimum spanning tree as a tree because the presence of any cycles within the tree indicates a redundant edge. For example, if every house is connected by water line, and there's a cycle among the lines present in the graph, then that means there's an edge that's present between two houses that's not really necessary, because the water could just go around the other direction, around the cycle, that is. So we could go about removing that edge and make it an acyclic graph, which makes it a tree. Let's go take a look at the whiteboard to see how that works. Once again, I've got my little neighborhood where I've got my own home as the root node of A, and then all the other nodes in the neighborhood B, C, D, E, and F. And my goal is to make sure that every node is connected to every other node in some way, such that it minimizes the overall cost of the graph to connect the nodes together. Every node needs a path to every other node, but that path need not be the shortest path. Instead, I just need to guarantee that there exists some path between one node and any other node in the graph. Prim's algorithm was discovered by Czech mathematician Wojtek Jarnik in 1930 for finding the minimum spanning tree. And what we'll discover is it's actually quite similar to that of Dijkstra's algorithm. We'll start out by initializing a connected vertex set S. That starts with the root node. S is going to represent the nodes that are already connected to the tree. Then we'll also initialize an edge set E that starts empty, which composes all the edges within the tree. Next, we'll initialize a priority queue of edges, and we'll call that Q, with all the root node's edges to start. And we're going to make the priority of each edge be the cost of each edge. This is where we see a distinction between how the Dijkstra's algorithm is written. Rather than maintaining a priority queue of nodes, where the priority of each node is best known cost, we're going to initialize a priority queue of edges, where that priority is going to be dictated by the cost of the edge itself. Then, while the vertex set is not yet equal to all the nodes in the graph, our goal, which is to fulfill this tree with all the nodes, is let's go ahead and pop off an edge. Let's call it X, which leads from V to U off the queue. And if U is already present in the connected vertex set, then we'll skip it. Otherwise, we will add U to the connected set. We will add this edge X to this edge set. And then for all the edges Y that are connected to U, that is all the edges that span the node that we are targeting, we're going to insert those edges into the queue. Then finally, we'll return the edge set, which represents our minimum spanning tree. Let's go visit the whiteboard to see how all this works. Okay, so I'll go ahead and use the skeleton graph on the lower left to represent our progress on the minimum spanning tree for the graph on the upper right. We will start out with the root node and have that part of our minimum spanning tree, and then we'll go examine all the neighboring edges of that root node and add those to the queue. The edge with the cheapest priority is going to be the edge from A to B with a cost of 2, so we'll go ahead and explore that one first. The algorithm tells us that when we explore that edge, we're going to ask ourselves if the end edge at B is already, the end node at B is already in the set, which it is not, so we'll go ahead and add that in, and then we will add the edge itself to the edge set. So let's go ahead and fill in that node to indicate it's already part of the tree, and I'll shade in the edge to indicate it's part of the tree as well. Then I go look at all the edges that all the edges that go out of the B node and add those to the queue. I've got the edge that leads from B back to A, as well as the edge that leads from B to C. To simplify this example, I'll go ahead and skip the edge that leads from B to A, because next time I get around to it, I'm going to end up skipping it anyway, because A is already within the connected vertices set. Okay, so that adds the edge from B to C into our queue, which leaves us with 3 more edges that we need to consider. The edge from B to C is the cheapest edge, so we will go pop that off the queue first. Once again, we'll add C into the vertices set because it's not yet present, as well as the edge from B to C. And then we'll go examine C's neighboring edges. C has 4 neighboring edges from C to B, which we'll go ahead and skip because B is already within the set. From C to A, which is actually present in the queue already, but we will end up skipping because A is already in the set. From C to D, and then from C to E. All right, we've got 3 edges in the queue. The edge from C to D is the cheapest edge, so we'll go pop off that one. D is not yet in the set, so we'll go ahead and add it, as well as the edge from C to D. And then we'll go look at D's neighboring edges. Once again, we've got edges that lead back up to nodes that are already within the visited set. D to C, we can ignore that one. D to A, we can ignore that one as well because C and A are already inside of our minimum spanning tree. D to E is a new one that we haven't seen before, as well as D to F. Okay, we've got 3 edges in our queue. The cheapest one is from D to E, so we'll consider that one first. E is not yet in the visited set, the minimum spanning tree that is, so we'll go ahead and add that in. And we'll shade up the edge that links those 2 nodes. Then we'll also have to examine all the neighboring edges of E. We've got the edge from E to C, which we can ignore because C is already present inside the minimum spanning tree. We've got the edge from E back to D, which we can ignore as well. And we've got the edge from E to F. Let's go ahead and add that into the queue. Okay. Next, our priority queue has 2 edges within it, E to F and D to F. E to F is the cheapest one with a cost of 1, so we'll go ahead and add F into the tree and fill in the edge from E to F as part of the tree. And we'll go examine F's neighboring edges. We've got the edge from F back to E, which we can ignore, and the edge from F to D. Once we get around to processing this last edge from F to D or any redundant edges that we see, we're going to go end up skipping those edges because the edge themselves don't add anything new to our minimum spanning tree. So the clever thing about this approach is that the algorithm is going to go figure out in a greedy fashion what edges are cheap as it explores, and connecting those edges if they join a new node that we haven't seen yet into our tree. This is why Prim's algorithm, I think, is not only effective, but not too challenging to understand. Unlike Dijkstra's algorithm, we don't really have to keep track of a local cost that it takes to reach every edge, every node. Instead, we just look around locally to see what's the cheapest thing that will get us to a new novel location and add that as necessary. The clever thing about this is no matter where we start within the graph, we're going to end up following the same approach where as we expand, in which we know we have to expand because every node has to connect back to every other node in some way, we'll go about going the cheapest way possible and always just pick whatever cheapest edges are currently present so far as where we've looked within the graph. So some observations I have written down here. Prim's algorithm is going to greedily add the cheapest edge connected to the tree. Prim's is going to avoid having cycles by checking if a vertex is already connected. And Prim's eventually processes every edge, but is going to skip the edges that don't add anything new to the tree. I like to say that Prim's is like a simpler Dijkstra's. It doesn't have to keep track of an extra table that maintains the best known cost to every vertex. Instead, it just asks if the edge connects something novel. And if it does, and it's the cheapest one we see, then let's go ahead and add it to the tree. Just like Dijkstra's, we know the big O of Prim's is going to be at least the big O of the number of vertices plus the number of edges, because we have to visit every vertex at least once, and we're going to examine every edge at least once. You made it! In this class, we have now seen every major data structure in computer science. Yay! We have the array, the primitive array, and its bigger brother, the array list, the linked list, as well as its variants, the doubly linked list, the stack, and the queue, the tree and the binary search tree, the heap, the hash map, and the hash set, and now the graph. I like to say that the best camera is the one that you have on you. And similarly, the best data structure, well, that's the one that best fits the problem at hand. Asking about what is the best data structure is kind of like asking between the trade-off of runtime and space. It is up to you as the engineer to make the call as to what choice you're going to make here in the context of the application that you're working on. Much of computer science research is based on how we can optimize these fundamental data structures. Are there more structures and algorithms to discover? Yes. The heap was discovered in just 1964, and the inventor passed away in 2012, which was not too long ago. Okay, you did make it. If you're listening to this, I'm proud of the fact that you've made it through all these videos and you've now explored all these data structures. We're not quite done yet with content in this class. You do have another project coming along, which I'll talk about in a briefing video. But I would say having a good understanding of all these structures is going to definitely benefit you in the long run, where you'll have a more certain understanding of how you're going to manage your data. And you'll get better insight into what kind of trade-offs we have to make in terms of runtime and space and complexity when making choices in your implementation. Okay, this has been a pretty long lecture. We've got a Project 4 briefing video coming up that's going to go over merging heaps and hash maps, so watch out for that. Thank you for listening. I'll talk to you next time.